All right, let's jump right into this explainer. Today, we're taking an incredible journey straight to the absolute heart of matter. We're focusing on explaining the core concepts of nuclear physics, specifically unpacking that fascinating chapter on nuclei. We're going to completely demystify the dense core that makes up our physical world, pushing way past the electron clouds to understand the hidden mechanics that, quite literally, hold the universe together.
You know, Rutherford's classic scattering experiments, right? Firing alpha particles at thin gold foils? Well, the results of those experiments completely flipped our understanding of atomic structure on its head. They showed us that the nucleus is incredibly, almost incomprehensibly tiny compared to the atom as a whole. So, just to put that in perspective for a second, if you enlarged an atom to the size of a standard classroom, what exactly is the nucleus?
It's a pinhead. Literally, a pinhead. It's a complete paradox of scale. The atom is almost entirely empty space. I mean, the volume of a nucleus is about 10 to the power of -12 times the volume of the entire atom. Yet somehow, this microscopic pinhead contains more than 99.9% of the atom's entire mass. It's a concentration of matter that almost defies logic.
So here's our roadmap for this explainer. We're going to cover 1. Inside the atom. 2. Protons, neutrons, and isotopes. 3. The mass-energy connection. 4. The strong nuclear force. 5. Radioactivity. And finally, 6. Unleashing nuclear energy.
Part 1. Inside the atom. A drop of liquid density.
So after bombarding targets with fast electrons in extensive scattering experiments, physicists realized something wild. Different nuclei basically act like a drop of liquid with a constant density. And that density is just immense. We're talking approximately 2.3 times 10 to the 17th kilograms per cubic meter. To really grasp that number, think about water. Water is just 1,000 kilograms per cubic meter. This extreme nuclear density is so vast that you can really only compare it to the matter found in distant neutron stars. Basically, the core of an atom is a microscopic neutron star sitting right here on Earth.
Moving on to Section 2, Protons, Neutrons, and Isotopes, the cast of characters.
Now, before we meet this cast, we absolutely need a new scale. Kilograms are just terribly inconvenient at this level. I mean, a carbon atom weighs a fraction of a trillionth of a kilogram. So we use the atomic mass unit, or U. It's perfectly defined as 1/12 of the mass of a carbon-12 atom. It just gives us a much cleaner, easier way to weigh these tiny characters.
And once we actually started weighing atoms accurately with mass spectrometers, we hit a curveball. We found variations, which introduced the concept of isotopes. Isotopes are just atoms of the exact same element that have the exact same chemical properties, because of course they have the same number of electrons, but they differ in mass. Take hydrogen, for example. It has 3 versions: standard hydrogen, deuterium, and the unstable tritium. They're all hydrogen, they just have varying amounts of neutral matter tucked inside their nuclei.
For the longest time, the exact nature of that neutral matter was a huge mystery. The positive charge obviously comes from protons, but what was accounting for all that extra mass? Well, James Chadwick solved the puzzle in 1932. By bombarding beryllium with alpha particles, he saw this neutral radiation that could knock protons right out of light nuclei. Using the laws of conservation of energy and momentum, he proved this wasn't just electromagnetic radiation. It was a brand new, neutral particle with a mass very close to a proton. Boom, he discovered the neutron, which, rightly so, earned him a Nobel Prize. Today, we just refer to both protons and neutrons collectively as nucleons.
Which brings us to Section 3, the mass-energy connection, the plot twist. Think about it like building a house out of bricks. Logic dictates that the house should weigh exactly the same as all those individual bricks combined, right? Well, in the nucleus, that just doesn't happen. Let's look at oxygen-16. If we weigh its 8 isolated protons and 8 isolated neutrons, the total mass is 16.12744 atomic mass units. But the experimental mass of a fully intact oxygen-16 nucleus is only 15.99053 U. The intact nucleus actually weighs less than the sum of its individual parts. No way, right?
So where on Earth did that missing mass go? We call this discrepancy the mass defect, and the answer is pure Albert Einstein. That missing mass hasn't vanished. It's been converted into energy. The missing mass is literally the equivalent binding energy holding the nucleus together. If you wanted to rip that oxygen nucleus back apart into individual protons and neutrons, you'd have to supply that exact amount of missing energy, about 127.5 MeV, right back into the system.
All right, Section 4, the strong nuclear force, the climax.
Okay, so we know how much energy is holding this thing together, but what is actually doing the holding?
I mean, why don't mutually repelling protons just blow the atom apart? We all know positive charges repel each other through the Coulomb force. To overcome that immense repulsive force inside that tiny pinhead, there has to be a completely different, overwhelmingly attractive force at play. That's the strong nuclear force. And here's what's so cool about it. It is massively stronger than the Coulomb force, but it's extremely short-ranged. It practically drops to zero beyond just a few femtometers. And fascinatingly, if nucleons get too close, under 0.8 femtometers, the force suddenly becomes strongly repulsive, which is what prevents the nucleus from just collapsing in on itself. Oh, and it completely ignores electric charge. The glue between two neutrons is exactly the same as the glue between two protons.
Section 5. Radioactivity. The resolution.
Back in 1896, A.H. Becquerel accidentally leaves some uranium salts wrapped in completely black paper sitting on a photographic plate. When he develops the plate later, it's totally blackened. Something had penetrated the opaque paper. That lucky accident revealed radioactivity. When an unstable nucleus decays, it resolves its instability by ejecting parts of itself, and this cleanly breaks down into three distinct types. Alpha decay emits a chunky helium nucleus. Beta decay shoots out a tiny electron or positron, and gamma decay releases high-energy photons just to shed some of that excess energy.
And finally, Section 6. Unleashing nuclear energy. The macro consequences.
Remember that mass defect we talked about? Well, it turns out nuclei of medium size, like iron, have the highest binding energy per nucleon. That means they are the most tightly bound and the most stable. Light nuclei and very heavy nuclei are just less tightly bound. So, whether a heavy nucleus breaks apart into intermediate pieces, which is nuclear fission, or light nuclei smash together to form a heavier piece, which is nuclear fusion, the resulting system shifts toward a more tightly bound state. And because the final system is more tightly bound, it has less total mass than the initial system. That tiny, tiny sliver of missing mass is unleashed as a tremendous amount of net energy.
To really put this into perspective, if you isolate just 1 kilogram of uranium for fission, you generate this massive number, 10 to the 14th joules of energy. Let that sink in for a second. Burning an equivalent 1 kilogram of ordinary coal gives you about 10 to the 7th joules. That means nuclear sources produce 10 million times more energy than chemical sources, for the exact same amount of matter. It's an absolutely staggering leap in power generation, purely by shifting the microscopic architecture of the nucleus.
And that wraps up our journey into the nucleus. Let's just end on this wild thought. The same invisible strong force that prevents a tiny pinhead of matter from violently flying apart right here on Earth is the exact same fundamental mechanism that releases the roaring energy powering the sun and every star in the night sky. We've gone from the tiniest fraction of empty space inside a classroom straight to the fiery engines of the cosmos, all tied together by a tiny bit of missing mass. So what else is hiding in the empty space of the atom? Keep wondering, keep learning, and thanks for joining me on this explainer.